Hi everyone, this is going to be a video about introduction to one way to understand what the intermediate value theorem is really about. So here's a statement of the theorem. I adjust it a little bit. It says if f is continuous on the numbers at the closed interval of numbers in between a and b, and if L is a number in between the function values at that endpoints, then there is a number that achieves this intermediate value exactly and precisely. This is not approximation statement. There's a number whose function value is exactly L. Usually the way to introduce the meaning of this intermediate value theorem is that using this continuity, the intuitive idea about the continuity. So if you believe we start from this function value fa, and continuously that changes to FB. Think about level of water or anything that you observe in nature or in physical phenomena, and you see some quantities changing. Because it's changed with respect to time, we naturally accept that it is kind of continuously changing. So think about some quantity is changing from FA to FB continuously, and L is in between somewhere. So if it continuously changed from FA to FB, maybe water level rose and got down a little bit and rose again and got down a little bit. By repeating all this process, eventually became this water level, the water became FB, for example. Then it changed from here to there. Was a phone interruption, but I'm continuing here. So this continuum of time or anything that we accept like space is mathematically about to be analyzed. And I think if you have studied the definition of continuity, and that's how mathematicians define this, the continuity. So yet we still wanted to understand this theorem more intuitive sense using the continuity, and the following is an example that our intuitive notion can kind of breaks down if you look at this example, and from that we hope you understand what this continuity really means. So I'm attacking this intuitive notion of continuity, and I'd like to introduce in an informal way and what a number line is. This number line I introduce is that I plotted, suppose this is a collection of all dots that are rational numbers. So we can call this is a number line of rational numbers. So this mathematical definition of this thing may be the collection of all the positions we can describe using these rational numbers. For example, think about the position 3/5. Now, for example, like this, suppose we have a position here, this 3/5, and what this means is that we can describe this position by this quantity, the length from the origin to that one. So, for example, if you divide unit length into 5 pieces, and then third, the part is the exact location of this one. So it is probably impossible to exactly pinpoint that the third unit, but you and I had fully understood that position in precise sense. So the collection of all the position we do understand is this number line, which is created by this way. This includes all the position and decimal expansion, and which eventually at the end had this repeating block. So that's the collection of all these numbers. Again, back then, this is the older number system they can understand. When they look at these rational numbers, it is very, very dense, and this is the key word I'm using, try to kind of replace this intuitive notion of continuity. I think when people usually say intuitively continuous, it's just there's so many numbers that are densely put together. If you choose any two numbers, there's always a number in between. They're all put together closely. And dividing given quantity into a finite number of pieces, and then understanding positions in this way back then before these irrational numbers were invented is the way we understand the number system. So maybe to some of us, and if you plot it like this and you cannot see holes or anything, it is impossible to define that hole in physical sense, but mathematically it can be. But if someone does not distinguish these two, this number line of rational numbers can be accepted as a continuum. Something is continuously put together. Later, people discovered the existence of position here. They can describe using the architectural or construction method. They can describe a position that cannot be described by this construction method. Therefore, in our mind, we can understand there's a precise position that is outside this realm of rational number system. So if this is true and there's a precise position this doesn't cover, and we can look at that as a whole, but in some sense, if you go back and did not think about it R and did not assume that we don't know about this number system, this is pretty much continuous, and you can imagine and all the numbers and pretty much we can think of is put together and create this solid looking line, so-called a continuum. So let me explain the notion of dense again. And if you look at the rational number, this is a bold-faced Q. In rational number, if you choose any two numbers, you can always find many other points in between, such as midpoints and third points. If you calculate that, they're still in rational number form. So they're very dense to each other, and this R has the same property. If you have two positions, there are always positions in between. So, and if I try to trick you that maybe the continuum is really this property of a dense, it's just there's so many numbers in between and there's no gap, which is not true. This has a gap, and although it's a dense, and we can precisely pinpoint that there's a position that this will never actually touch. So we have to distinguish in that way what a continuum and a dense sense. But if you didn't know about this real number, again, you might be tricked by this dense as an intuitive notion of a continuum, because they haven't found this position that this Q doesn't touch yet. So I'd like to claim that intuitively, and there is no problem with considering this number line of rational numbers and as a continuum objects. Namely, it's dense. But that's not the correct notion these days because we have discovered it. But let's say we were kind of equating this dense and then continue at the same time. Let's see what happened. Then I want you to think about the graph. The graph of f of x, where x varies over these rational numbers, is also continuous. If you actually schedule, think about the computer program, they actually went through a very small number of, actually finite number of rational numbers, and they sketched a graph. And from that, and we can throw in more and more points in between. Even that process, still we can remain in the queue. I think that's pretty much how we intuitively comprehend the continuity. But it's actually in this world right here, and you're putting in all the rational numbers, and we're sketching those graphs, and from the computer you can imagine this is very continuous curve. Now suppose, think about the function sends rational number to rational numbers, such as a polynomial and something like that. And in that case, we can, just like we define the continuity of a function on the real lines, we can do the same thing. And if the limit x approaches to a rational number, this means x is approaching this rational number p along with some arbitrary sequences of rational numbers. If the function value of a limit is the same as function value of p, we define as continuous local continuity of this function, just like we did for the real line. And we can use this to define the global continuity. Let I be an open interval of rational numbers in between a and b, and we're going to say the function is continuous on the interval I. If the function is continuous at every point in I, these are rational numbers. And think about the situation like this. The function is x cubed plus x plus 1, so this x line here is the points of all rational numbers. And in our ability to zoom in how much we can zoom in, there's no way to detect the holes or anything. And if you look at the graph of these functions, it's going to be continuous like this. So now let me remind you of the intermediate value theorem one more time. And if this is following: f is continuous on the real line, real interval, closed interval, a to b, all the real numbers. And if f is continuous, then f of x, and if L is an intermediate value in between fa and fb, then that intermediate value will be exactly achieved as a function value. There is some number, if you plug in, it precisely becomes L. And this is about to be it fails when we look at this different continuum in here, a to b. So first, let's look at the continuity property. This f of x equals x cubed plus x plus 1. Turns out it's a continuous function on the closed interval of rational numbers in between -1 and 0. So not irrational numbers, rational numbers. So again, in our intuitive notion of a continuity still holds nicely, and if by looking at the pictures and everything. And if you look at f of -1 and f of 0, then this f of -1, if you plug in x equals -1, you get -1, and x equals 0, this function value becomes 1. So 0, the L here is a 0. The L0 is intermediate value of this function, two function values. So since these guys are continuously changing from -1 to 0, -1 to 0 here, it's going to pass through L0. And that's the idea of the intermediate value theorem. And if you don't see why that's a theorem, and then if it is something obvious, and then you were looking at this result and an obvious thing, because this is continuously changing from -1 to 1, and it must pass through 0, and that's the result of intermediate value theorem. Something obvious from our intuitive notion of continuity, which is often represented like this. The graph looks like continuous here from -1 to +1. The function value changes from there to continuously to the +1 as x values from -1 to 0, continuously changing over these rational numbers, the numbers we understood back then in ancient time. However, it is the fact that there's no rational numbers in the entire line of the rational numbers, that if you plug in this c into this function, which is x cubed plus x plus 1, then you get this intermediate value 0. This is called rational zero theorem. If you use that, and you can easily show that this polynomial does not have rational 0. So again, if you thought the lesson about this thing is that if you thought the continuity, which we in everyday sense we usually identified as a dense property, and if that intuitive notion of a continuity naturally leads you to, okay, I'm continuously changing from here to there, and it's gonna cross this one in a precise value there, and it says it's wrong. It's not because of that. And what is really making this intermediate value theorem true then? The real theorem requires this line to be real line. So this continuity, the continuum property, must have this real number structure, not just that our everyday notion of the continuity, the dense property. So that property, that fancy property, is called completeness of the real numbers. So if we don't understand the phenomenon of intermediate value theorem without really using the complete property of the real numbers, your thinking is not precise, not intuitive actually. So that's what we have to think about, and that's how we should look at this intermediate value theorem.